So thanks everyone for coming here. For the past 1 year, we've basically been social distancing. I like this graphic. And no sooner do you see the words distancing when a bunch of geometers will pop in and make up interesting problems and try to solve them. So that's what I'll be talking about today. It's how to stay socially distant, a geometric approach. This is ongoing joint work with Joe at Stony Brook, Joe and Omrit at Stony Brook, and Valentin at Linköping University. But I'll start with the general class of problems, the definition. So these are all social distancing related problems. So in the most general setting, you've got K agents. For now, let's think of them in the plane. And each agent has some domain of movement, and these domains could be shared. So for example, this agent maybe is allowed to move inside this ellipse. The other agent is allowed to move inside the polygon. This agent has a rectangle that overlaps with the polygon. Maybe this agent is only restricted to move on a curve. This agent is doing a tour. And my animation skills are not good enough to show it, but the agents could have different speeds, right? So now it's not necessary that all agents are moving with the same speed. And we need someone to do we need some movement, right? Because if no one is on a mission, then they can just stay where they are. So we'll assume that at least one agent is on a mission. So maybe this guy has to go on this red curve, and he has to visit these areas, which will then require these people to sort of move away. So our goal is to find the movement strategies so that we maximize the closest that any two agents come at any point of time. Okay, so you've got some agents are on a mission, some agents are just trying to stay away, and we want to devise strategies so as to maximize the minimum pairwise distance between the agents at any time. And we want to avoid trivial solutions of the type one person stays home while the other person finishes its business, and then only does person one leave. So sometimes it's also good to have some sort of make span bound that all the missions should finish within a given time t. So you're not waiting a million years for someone else to finish their mission. So that's a general class of problems. And it is related to like a lot of things that have been done in computational geometry before. So first thing, it may not be clear why it's related to the fresh air distance. I'll talk about it later. Because in fresh air, the man and dog are trying to be close together, whereas here we're trying to be separate, but it is related to fresh air distance. More importantly, it is related to motion planning, where there has been work on either coordinating two disks, right, that are moving in the plane, or very recently, you're reconfiguring a swarm of robots. So you have a bunch of robots, and so a robot has a starting point and a final point, and they're trying to find trajectories to go from the starting point to final point while not intersecting any other robot. So it's related to motion planning. It's also related to this asteroid avoidance, studied by Reef and Shari, which is you have an asteroid, it's, I think, translating, and there's a bunch of other objects that are trying to stay away from the asteroid. It's also related to air traffic management. So you're trying to find thick paths in either a static or a dynamic environment. The static version of the problem, where you just have static points, that's called the maximum dispersion problem. So you try to find a set of points that are as far apart as possible. So that has been studied fairly well in literature. There's also some work on dispersing robot swarms in unknown environments. And lastly, it's also reminiscent of the lion and man type of problems, where you have a lion that's trying to get to a man, and the man is escaping from the lion. And depending on whether the lion is faster or the man is faster, you ask questions of the form, can the man ever evade the lion? It's different from our setting in the sense that no one is, there's no adversary in our setting. So maybe someone is on a mission and the other people are just trying to stay away. But the mission is never to sort of infect the other person, right? So the mission is just traversing some curve, or maybe going through a set of points. But the mission is never to come close to another agent. So in this talk, we'll only study the case of two agents. That's already pretty interesting. And we look at different kind of domains. So three types. So first we'll look at the case where agents are moving on just curves. Then two agents in a polygon. And then we'll also look at agents moving on a graph. And the graph could be either geometric or non-geometric. So we'll talk about it soon. And please stop and interrupt me with any questions that you may have at any time. So what we'll be doing is we'll define this concept of social distancing width, and then we'll talk about algorithms and lower bounds. So let's talk about curves first, right? So just two curves. So given two curves, a red curve and a blue curve. And by a curve, I mean a polygonal chain, basically. So you've got two curves P and Q, just represent them as continuous functions from the interval 1n to d dimensions. And since they are polygonal chains, they're restricted to an interval, an integer interval, the curve is a line segment. So this is P of 1, that's P of 2, and part of curve between P of 1 and P of 2 is a line segment. This is Q of 1, and that's Q of n. Okay. We'll need to define traversal of curve. So a traversal of a curve is just a parameterization of the curve. So you've got two functions f and g. These are just continuous and non-decreasing onto functions from the unit interval to your curves. Non-decreasing here means that the people who are walking, they're not allowed to, the agents walking are not allowed to backtrack. And surjections basically means you have to traverse your whole curve. Right? You can't just traverse part of it and then say you're done. So now here's the definition of the social distancing width. So two agents, the social distancing width is defined as you take the supremum over all possible traversals, f and g, of the two curves, P and Q. And once you fix a traversal, you look at what is the closest distance between the two agents at any time. And you're trying to find the traversal which maximizes this distance. So it's basically how do the agents walk in order to maximize the minimum distance at any time between. Now, this may remind, so before that, so maybe the blue agent here is at time half is at this vertex, and the red agent at time half is at this vertex. So we look at the distance. This is how close they are at time half. And we are trying to find a way for the agents to traverse their curves, which maximizes, the closest they have a curve. This may remind some people of the Frechet distance, and it's actually a flipped version of the Frechet distance, which makes it interesting. So to remind what the Frechet distance is, this is it's classically posed as a problem where a person is walking a dog. Let's say the person is walking on the blue curve and the dog is walking on the red curve. And what you want to do is you want to find a way for the person and the dog to finish their walks in order to minimize the maximum length of a leash. So given a traversal f and g, this term here is how long the leash needs to be if the person is walking according to f and the dog is walking according to g. And then you're trying to find the way to walk so as to minimize the longest leash length. So if you compare the social distancing width to the Frechet distance, it's a flip, right? So this is sort of a min-max, and it's being changed here to a max-min. And so this is why I mentioned that it is related to the Frechet distance. Here's the definition again once. As I mentioned, it's a fifth version of the Frechet distance. We can't really call it a distance because it's not a metric. So if you look at this example, we have three curves here, P, Q, and R. The social distancing width between P and R or between Q and R is just epsilon, right? Because if an agent is walking on P from left to right, and another agent is walking on R from right to left, what this agent has to cross, the agent at P will cross the agent at R at some time, and their distance will be epsilon. Similarly, the distance between the agent Q and agent R will also be epsilon. However, the distance between P and Q, they both could move sort of in parallel. They could translate together. The distance between P and Q is a constant. And so you see here that it doesn't satisfy the triangle inequality. So it's not a metric. So think of it as more of a measure of, so it's a distancing width. So it's a measure on how easy it is for two agents to maintain social distancing while traversing these curves. Now, what I state above here is the continuous version because my traversals were from the continuous interval to the curves. But there's also a discrete version where instead of sort of the person walking the dog continuously, you can think of, I think some people call it as frogs hopping. So you're not traversing the curve, the continuous curve, but you're just hopping from one vertex to another. And in this setting, traversal is basically a sequence of pairs. So locations of the first agent and the second agent. And the sequence satisfies the property that they must both start at the first vertex. So the first frog starts at P of 1, the second frog starts at Q of 1. They must end at the last vertex. And from any position ij, you can only have one of three possibilities. Either the red agent moves, so ij plus 1, or the blue agent moves, so I plus 1j, or both of them move together. Okay? So this is sort of a discrete version of the traversal. And we can also define the discrete social distance curve in that you want to find the traversal tau that maximizes the closest that these two agents have apart, where now the distance is only measured at the vertices. Right? So you don't measure the distance between arbitrary points on the chain, but only once the agent is at the vertex. So we've got two notions: a continuous social distancing width and a discrete social distancing width. And first, I'll talk briefly about algorithms. So one of the most important things for algorithms in either the Frechet distance or for our setting also is the free space diagram. So for those who haven't seen the free space diagram before, let's say you've got, these are your two curves, and here's a parameter delta. So the free space diagram of these two curves of range delta is a partition of this box, and the box is the cross product of 1n through 1n. And it's a partition of this into free and forbidden regions. In the free region, so a white point is a free region, and that corresponds to a pair of locations of the agents where the agents are at least delta distance away. So this is the free space, and it's the set of all points PQ, where if the first agent is at point P and the second agent is at point Q, then they are at least delta. So these vertical lines, they're basically showing where the edges of these curves are ending. So one sort of segment here, line segment here, corresponds to one line segment on the curve. And so this is the free region, and the complement of the free region is forbidden. So in this diagram, the forbidden region is shown in pink, and the free region is shown in white. This cell, for example, corresponds to the first edge of the first curve and the second edge of the second curve. So we call it CI2. And one of the observations is that if you just look at the set of forbidden points inside a cell, that's convex. So the intersection of pink region with any cell is convex. And that's a property that will be used later. And I remark that this property is exactly the opposite of the property that Frechet free space diagrams have, because in Frechet, it's basically the complement. So if it's less than equal to delta, then you are free, and that would be, so the white region would be forbidden for Frechet, and the pink region would be the free region for Frechet. All right, so now that we know what a free space diagram is, we can quickly summarize what the algorithm is. So we have an n squared log n time algorithm to compute the continuous social distancing width of two curves. And so the first step in this algorithm is it's enough to show to first figure out the decision version. So given a parameter delta, can blue and red maintain distancing at least delta? And once you solve the decision version, then you can basically an extra log factor, and you can solve it. You can actually compute the largest delta that works. And to solve this decision version, it's equivalent to deciding if you can go from the left bottom corner of this free space diagram to the right top corner of this free space diagram. And in order to do that, it's a reachability problem. So we build a graph, and one of the observation is because the forbidden region inside a cell is convex, there's only these 8 ranges that you really need to consider. So for at most 4 horizontal and at most 4 vertical ranges. So the original graph the original free space diagram had complexity n squared. It only increases by a constant factor more once we sort of add these edges. And so this graph will have size order n square, and then you can solve a reachability problem in linear time in order n square. So the decision version can be solved in n square. And then what you can show is there's not there's only a polynomial many values of delta to consider. So there are at most n cube values for delta. And then parametric search gives you this extra log n factor, and you get the n squared log n time algorithm for computing the continuous social distancing width. I also remark that this is similar to the classic Alton Grau pressure distance computing algorithm, except 2 differences. One, the flip thing. So R forbidden is their free is R forbidden. And these, the critical values are not exactly the same. So there's one type of critical values that there's an extra type of critical value that can occur in our setting that cannot occur in their setting. But other than that, it is pretty similar to the Frechet computation. And this is a quadratic, slightly more than quadratic time algorithm. We also have algorithms for other variants. So the one I just mentioned was the continuous social distancing width. For the discrete version also, you can give a similar dynamic programming algorithm that's also quadratic time. We can talk about approximations. So here, a factor F approximation means giving a traversal where red and blue maintain a distance at least F times that of the true social distancing width. And we have, so for Frechet also, there were similar approximation algorithms, and we can sort of extend them to the social distancing settings. For continuous, unfortunately, we don't have an approximation algorithm. That's also, so I think it's, we only have sub-exponential approximation algorithms for the continuous pressure distance. I don't think yet we have a polynomial approximation factors. So that's open. And then we can also solve the weak versions. In the weak version, the agents are allowed to backtrack. And either one or both agents are allowed to backtrack. And both of these versions can be solved. One thing that we don't know how to solve is this version of partial social distancing width, where one agent has to traverse the curve. The other agent can only do bits and pieces of the curve. And you're trying to maximize the total length of the other agent's pieces that are matched to the first curve. So this is a setting that we haven't looked at in detail yet, and so this one is still open. I think it was only recently solved for the Frechet. Right. So with all these quadratic algorithms, the obvious question is, well, can we compute the social distancing width in subquadratic time? And there's related work for Frechet. This was one of the breakthroughs in hardness in the hardness in P literature, where Brigman in 2014, he showed that Frechet, you don't have any, well, it's unlikely to have strongly subquadratic algorithms unless this strong exponential time hypothesis fails. I'll be describing what this hypothesis is in a moment. And then these results were also extended to 1D setting. And it's not just exact computation is hard. Recently, it was also shown that even computing it in some quadratic time up to factor 3 is will contradict the strong exponential time hypothesis. So we'll be looking for conditional lower bounds on our social distancing problem, and it turns out that it's a similar answer for our problem also. It's very unlikely for almost all variants of the social distancing problem. So what I mean by very unlikely, so this is a fairly recent field on conditional lower bounds, also called hardness in P. And one of the popular hypotheses in this field is Seth. We'll just work with a slightly different variant of Seth. So that's Seth prime, where if phi is a SAT formula, conjunctive normal form, you've got n variables and m clauses, then there is no basically 2 minus delta to the n algorithm to decide satisfiability. And this O star is hiding polynomial factors in n, which is again the number of variables, and m, which is the number of clauses. So this is a hypothesis that is believed by many people. And under this hypothesis, we try to give conditional polynomial lower bound. So here's our result. If you had a subquadratic algorithm for any of these variants, then that would violate this strong exponential time hypothesis. And what are the variants? So for 2D, both discrete and continuous social distancing width are subquadratic conditionally hard. In fact, they're even hard for approximation factors. For the discrete, anything better than 0.86, and for the continuous, anything better than 0.92. For 1D, the discrete setting is subquadratic hard, but surprisingly, we find that in 1D, the continuous setting is not subquadratic hard because there is a near linear time algorithm for the 1D continuous social distancing. So this is a summary of the lower bounds for the Casement 2 agents or on curves. And maybe I'll take about 5-10 minutes to show you this proof, so a proof of this conditional hardness of the 2D discrete and continuous social distancing width. And I'll start with a general outline of the proof. So basically we have to construct two curves. So given a formula, we'll construct two curves. Both curves will have these many vertices. So remember, m is the number of clauses and n is the number of variables in your SAT formula. There's an n over 2, so let's just assume n is even, the number of variables is even, otherwise add a dummy variable or something. So each curve will have these many vertices, and the two curves will have the property that if the red and blue agent, so the R is for the red curve, B is for the blue curve, if they can maintain a social distancing width of 1, so if they can always stay at least 1 apart, so that's if and only if the formula is satisfied. And what that would imply is if you had a subquadratic time algorithm for the discrete social distancing width, then you see that this thing would be a sub-exponential algorithm for SAT. So it would violate the strong exponential time hypothesis. So that's how you get the conditional lower bound. So if you can construct two curves such that this property is true, right? That the agents are able to stay away if and only if the formula is satisfiable, then we are done. So in order to go about this, what we do is we split the n variables into two groups of size and half. And A1 is the set of all possible assignments to the variables in the first group. And A2 is the set of all possible assignments to the variable in the second group. So since there's n½ variables in each group, you'll have 2 to the n½ possible true-false assignments to the variables in each group. And now this is what an assignment gadget will look like. So I'll first describe the assignment gadget, and then I'll build the complete curves. So let's say your SAT formula looks like this. So these are your m clauses. Now, given an assignment on the first n½ variables, so let's say your assignment looks like true, false, and so on. And given another assignment on the second group of variables. So the first assignment is sigma, and the second assignment is sigma prime. So blue is going to sort of go according to sigma, and red is going to go according to sigma prime. So let's see how blue goes. So blue starts from this point, which is the point half comma 0, and we have these 4 points. So this is the x-axis, and that's the y-axis. And this point is slightly below half, and that point is slightly above half from the origin. And similarly, this point will be slightly less than half from the origin, and this point is slightly greater than half from the origin. And now what blue does is, blue starts from the bottom, and the first sequence in the first point in the sequence of blue after the starting point is the below point if blue's assignment satisfies the first clause, or it'll be if it does not satisfy the first clause, then it would go to the top point. And then from this point, blue would go on one of the top 2 points, and it would go on the lower of the top 2 points, if its assignment does not satisfy the second clause. Otherwise, it would have gone to the top row, right? And so blue does this, right? So blue will basically hop back and forth between one of the top 2 points and one of the bottom 2 points. And because we are assuming that the number of clauses is even, and blue starts from the bottom 2 points, blue is going to finish on one of the top 2 points. So that's what blue's assignment gadget looks like. And similarly, we can define red's assignment gadget. It's the same, except red starts on top. So red will start on top. So if red's assignment sigma prime doesn't satisfy the first clause, then red goes to the bottom of the 2 points. And then it goes to one of these lower 2 points, depending on whether its assignment satisfies the second clause. And again, the number of clauses is even. Red starts on top, so red's going to finish on bottom. So basically, this is what the assignment gadget is going to look like. So blue will start from here. It'll visit either this point or this point, and then it'll go back and forth, right, for m rounds, which is the number of clauses. And similarly for red. And what one can see is, if the pair of assignments satisfies the formula, then blue and red can maintain a distance of 1. Right? It's basically because they move sort of opposite each other. So because this assignment satisfies, right, at least one of the clauses is satisfied by these assignments. So if red is on true, blue can be on false, or if red is on false, blue can be on true, right? Because at least for every clause must be satisfied by at least one of the assignments. So what you can show is, if the pair of assignments satisfy the variable, then they can stay one apart. On the other hand, if the pair of assignment does not satisfy the formula, well, then there must be a clause that is not satisfied by either of the assignments, and then blue must be at the false point and red must be at the false point for that clause, and then their distance is smaller than. So this is for one assignment, a pair of assignments. And now, so what does the full curve look like? So let's say L is 2 to the n half. And so first thing we do is, so recall that A1 is the set of all possible assignments to the variables in the first group. So blue's final curve we'll build according to A1. So what's blue's sort of point sequence? Blue will start from this point S1 that you see on the top right here. It'll go to B. Once it is at B, it will start doing its assignment gadget. So first, it'll do it for sigma 1, and then sigma 2, and so on. So let's say blue started its assignment gadget for sigma I. So the assignment gadget is, again, it'll go to one of these 2 bottom points, and then it'll jump back and forth, up and down for m times, and it'll finish somewhere on top. And once it finishes, it goes back to T1, then goes to S1, then comes back to B, and then it starts the assignment gadget for the next assignment. So blue basically makes a round, comes back to S1, and then starts the new assignment gadget. So that's what blue's sequence of point looks like. It'll do sigma 1 first, come back to S1, sigma 2, then come back to S1, and so on. Now, what about red? So red has its assignments enumerated for the second half of the variables. And what is red's point sequence? So red will start at X. It'll go to this point, S2. Then it'll come to this point R. From R, it'll start its assignment gadget. So remember, in red's assignment gadget, red starts from top and then goes back and forth for m times, will finish somewhere on the bottom. And from there, it goes back to R. And then it starts its next assignment, goes back and forth, goes back to R, starts the next assignment. And once all of the red's assignments are over and it's back at, it'll finish somewhere on the bottom. From there, it goes to this point T2, and it goes back to X. So that's what the red curve and the blue curve look like. And one thing that is sort of easy to show is that if there is a pair of partial assignments that together satisfy the formula, then red and blue can work so that they always maintain a distance 1 between them. And how do they do this? Well, so red stays at X while blue starts from S1, goes to B, and blue does all of the assignments that it has to do until it is just about to start the actual one, the satisfying assignment. And it doesn't start it, blue waits at S1. So blue has sort of finished all of its useless assignments and it's waiting in S1. And in all this, it didn't come within distance 1 of red because red is staying here at X. Now red starts while blue is at S1 and red goes to S2, which is distance at least 1 away from S1, goes to R, and then red finishes all of its useless assignments and comes back and waits at R. Okay, so now red and blue have both finished their useless assignments. Red is waiting at R, blue is waiting at S1. Blue moves to B, no problem, because distance between B and R is 1. And then they move in the opposite fashion, because now they're doing this satisfying assignment. So they can move in the opposite fashion, and they'll be able to finish all the M clauses. And after finishing, they can go back. So if there is a pair of satisfying assignments, blue and red can maintain a distance 1 from each other while traversing their curves. What is slightly harder to show is that if if blue and red can maintain a distance 1, then there must be a satisfying assignment. And I'll just summarize the proof in a minute. So let's say blue and red can maintain a distance of 1. Then notice that red must be at S2 at some point. And when red is at S2, the only place where blue can be, because of the way the distances are arranged, is S1. So when red is at S2, blue must be at S1. And regardless of what red does, at some point it has to come to T2. And when red is at T2, blue must be at T1. So which means in between the time that red was at S2 and T2, blue moved from S1 to T1. Well, then it must have gone through B. But when blue is at B, the only point red can be is R, because that's the only thing that's distance at least 1 away from B. And red is at R only before starting an assignment. So now red and blue must start a new assignment, and they must move sort of opposite each other. So that shows that if there is a satisfying assignment, if there is a traversal, then there must be a satisfying assignment. So I mentioned this. So let's see. Right, so this is basically what I just said written down. So they can maintain a social distance of 1 only if and only if there exists a pair of satisfying assignments. You can arrange the points and actually show that if the formula is not as satisfiable, then they cannot maintain a distance better than this. And this is basically you arrange points in a way so that the best red and blue can do, if there is no satisfying assignment, is no better than this. And what this gives us the approximation hardness. So because any algorithm that not only computes the social distancing width exactly, but even approximates it better than this factor, will be able to distinguish between these two cases, and then it can be used to solve SAT. So for the discrete, we get this factor. And in just one slide, let me summarize what goes wrong with the continuous. Well, the same construction doesn't work for the continuous, because when in continuous, blue has to move continuously from bottom to top, and red has to move continuously from top to bottom. And you just send them vertically up and down, they'll cross each other. So one fix could be that you could make red go this way and blue go that way. But that creates a problem because previously red was at this point only before starting an assignment, but now red is at this point even between clauses, and that's a problem because that won't give you an honest traversal. Red could finish some of its clauses from one assignment with blue, and then some of the clauses from the next assignment with blue. So you can fix this by replacing a circle with an octagon, and you can show the same thing, that if the formula is satisfiable, then there is a traversal, a pair of traversals, a pair of assignments, and therefore red and blue can walk while maintaining distancing 1. On the other hand, if there is no satisfying assignment, then the best red and blue can maintain are one of these 3 distances. So then in the lower bound, you basically arrange the points so that these 3 distances are equalized, and that gives you this factor. So the best red and blue can do if there is no satisfying assignment is 0.91, and this shows that if you have an algorithm that achieves better than a 0.92 factor, then that also violates SET. So there's a summary of the lower bounds for discrete and continuous 2D version in 2D hardness. So again, so now I'm going to summarize both algorithms and lower bounds. So we have roughly quadratic times algorithms for most variants. We have a subquadratic conditional hardness for the 2D discrete and continuous, the approximation factors. We also have hardness for 1D discrete that comes from the orthogonal vectors, which is also conditioned on set. And we can also prove hardness for the 2D weak discrete, where they're allowed to backtrack. Both are allowed to backtrack. And what I will not go into is this surprising result that in the 1D continuous case, we have a near linear time algorithm. And this basically makes use of the fact that, red and blue can never cross each other. So if you start in 1D, red starts to the left of blue. First, you can reduce the decision of distancing one to decide if they do not cross. And that can be checked in near linear. So that, right, so they cannot cross and they cannot switch sides. So that brings me to the end of part one. And let's see how I'm doing on time. Okay. So the last two parts are not, I won't have proofs. I'll just give sort of a summary of the results in our setting for the polygons and our setting for the graph. So for polygons, we have, so you got a polygon shown here in yellow, and we've got two versions. So the first version is you have red that's going about its mission. So red's mission is this path gamma that red is traveling, and blue is just trying to stay away from red. Okay, blue is not on a mission and is just trying to stay away from red. So red's path is gamma inside some polygon P. How far can blue stay away from red? Now, as soon as we talk about distance, you can talk about two versions, either the geodesic or the Euclidean distance. And you can also ask, well, is gamma actually a shortest path? So is red in a rush, or is red just going about some path? And another variable is how fast does blue speed compared to red's? We will be considering the version where blue is not speed constrained for that. So that's what we'll be talking about. So that's the first problem, blue distancing from red on a mission. And the second problem that we'll consider is how do you define the social distance width of a polygon? And then how do you compute? Okay, so let's talk about the first problem. So the first one, what we can show is if red is basically in a rush. So in other words, if gamma is a geodesic, so red is traveling from some point R to a point R prime on the geodesic, then the decision version, whether blue can stay one away from red, can be solved in linear time. So here's a picture. Here's red, starts from R, it's going to R prime via shortest path gamma. Blue starts from some point B. And in linear time, you can decide if blue can maintain a distance of 1 from the red. So I'm not going to go through the proof. The proof basically uses this fact that if you take a point, and the geodesic distance from a point to a geodesic path is a convex function of the point on the path. And using this is the main fact that we use, and the proof is by contradiction. The linear time algorithm uses this shortest path map developed by Leo Gibas and Hirschberger, and can be built in linear time. And that's how we decide if blue can stay distance 1 from red, if red is moving on a geodesic. If red is traveling on an arbitrary path, then the best we can do is quadratic time, which is pretty simple. But we don't have lower bounds here, so we don't know if red is traveling on an arbitrary path, do you need quadratic time to decide if blue can stay a distance one way? And the lower bounds, that's conditional. I mean, it has to be a conditional lower bound because we're talking about quadratic hardness, but we don't have that yet. Again, the above result assumes that blue can travel sufficiently fast. So the speed bounded version of this variant is open. The second problem on polygons that I mentioned is how to define the social distancing width of a polygon, right? And how to compute it. So in this setting, well, I mean, I'm sure you can define it in other ways, but the one we thought was most meaningful was red and blue are both moving on the boundary of a polygon. So red is moving over here, blue is moving here, and red moves, let's say, clockwise in unit speed. Now red could either be just doing one round of the boundary, or it could be doing many rounds. Maybe this is what red is doing all its life, just patrolling the boundary of the polygon, and it's moving clockwise with constant speed. Blue, all blue is trying to do is to stay a distance delta away from the red. And blue can backtrack. And for now, let's assume blue has unbounded speed. Most of the bounded speed variants are much harder to solve, and we don't know how to solve them in most settings. So for now, let's say blue has unbounded speed. It can backtrack, and all it's trying to do is stay delta away. And now, as soon as I say stay delta away, you can again ask, well, Euclidean or geodesic, and you can define the Euclidean social distancing width or the geodesic social distancing width of a polygon to be the largest Euclidean or geodesic distance delta that blue can maintain from the red who's going clockwise around the boundary of the polygon. And we choose the version where red is doing multiple rounds because that's slightly harder, and we can also solve the version where it's doing one round. And for this version, we show that the social distancing width can be computed in roughly quadratic time. And this setting is one that doesn't really make sense for the fresh air, right? Because here both agents are moving on the same curve. So in fresh air, they would just stay with each other, right? You don't need any leash. The man and dog could be on the same point. But here they're trying to stay away from each other. So you can again build a free space diagram, which is what is shown on the right. Notice that the diagonal will always be forbidden, right? Because diagonal corresponds to both agents being at the same time, being at the same point on the boundary. So the pink region is forbidden, and a strategy basically corresponds to a sequence. So red has to start somewhere from the bottom, and because this is a simple closed polygon, these two vertical sides are identified, and the two horizontal sides of the free space diagram are identified. So when red hits here, red can continue. When the curve hits S1, it'll continue from the left side, and if it hits this point S2 on top, it'll continue from the bottom edge. And the algorithm basically makes use of the free space diagram. It looks for Y monotone path. Y monotone because red is not backtracking, right? Red is going clockwise with unit speed, but blue is allowed to backtrack. So you only have paths. So you have a Y monotone path, and if you look at this Y monotone path, right? It could be complex, but because of the convexity of the forbidden region, what you can do is you can snap this Y monotone blue path to sort of the L-shaped red path. And so by snapping to the bounding box, we can solve again a reachability problem in roughly quadratic time. So that was sort of a brief summary of the results on polygons. And the last section is on graphs. And we consider two types of graphs: geometric graphs, which are more interesting because there's more geometry in them, and also non-geometric graphs, which are just plain unweighted, undirected graphs. So let me first quickly summarize our result for the non-geometric graph. So what's shown here is a non-geometric graph, which is all weights are 1. It's undirected. Red is traveling on a known path of length k. And in this version, we can actually look at the bounded speed variant. So blue has a speed that is some factor s times that of red. So what that means is in the time that red makes one hop, blue can make s hops. And now the question is, can blue stay a distance delta away from red, who's traveling on a known path in this graph of length k? And for this version, we can show that, well, if blue speed is equal to that of red, so if s is 1, or if blue speed is way faster than that of red, so if s is n minus 1, then in k times m time, so m is the size of the graph, and k is the length of red's path, we can decide if blue can stay delta away. And if your factor s is some arbitrary number between 1 and n minus 1, then we also have an algorithm. Unfortunately, the dependence on s is exponential, which is tragic, but This is what we have right now. And as I mentioned, the bounded speed variance in most settings, even for Frechet, are sort of harder to solve. That is all I'll say for the non-geometric version, because what's more interesting is the geometric graph version. So by geometric graph, I mean a plane graph. So it's embedded in the plane. And we'll consider, so the weight of an edge will equal the Euclidean length of the edge for us. And so first, let's look at the setting where sort of blue is trying to stay away. So blue is restricted to stay on this graph, and it's distancing from red. Now, question is, where is red traveling? So red could travel either on the graph or on some other polygonal curve. If red is traveling on some other polygonal curve, then the only version of distance we can talk between red and blue is the Euclidean distance. And in that setting, we can again decide in basically quadratic time, so size of the graph times size of red path, whether blue can stay delta away from red. If red is walking on the graph, then you can not only talk about the Euclidean distance between red and blue, but you can also talk about the geodesic distance between red and blue. Geodesic distance on the graph. And this result that I stated also works if red is walking on the graph and the distance is Euclidean. And now for the geodesic version, so we define, so this will be the last definition. So it's the social distance width of two graphs. So in the first part, we saw, well, how similar or different are two curves, but where similarity is measured using the social distancing width instead of the Frechet. And now this is sort of an extension, a generalization to graphs. And it's not that the same problem has not been looked at for Frechet. So there have been at least a couple of papers that have been focused on generalizing Frechet distance to graphs. The first paper is on matching planar maps, and they define this traversal distance. So it's a distance between graphs, which generalizes the Frechet distance to geometric graphs. Our setting will be similar to here, except for Frechet, we'll have this social distancing width, the flipped version. There's also another paper that I'd like to mention by Akidaya et al. And it's called Distance Measures for Embedded Graphs. And they define graph distances that are sort of more combinatorial than the above traversal distance. And their distance is defined in terms of mappings between graphs. And their mapping takes a vertex of one graph to a point on an edge on the second graph. But it's allowed to take an edge on one graph to a simple path on the second graph. And that makes sense in Frechet, because sort of the dog will never need to loop around, but it doesn't make sense for us in the social distancing setting, which is why right now we are focusing on similar settings as the first traversal distance definition. So what's the setting here? So the traversal, so first let's define what a traversal of a geometric graph is. So a geometric graph will just be identified with the points on the edges. Right? So it's basically a metric space composed of all the points that lie on the edges. And a traversal of a graph is a continuous mapping from the unit interval to the graph that is onto. So when I say traversal, I will mean an onto mapping, which means all points of the graph must be mapped. Now notice that traversals will need to backtrack sometimes, right? If you're hitting a vertex of degree 1, then there's no way to continue your traversal without backtracking on that edge. So traversals will be allowed to backtrack, which is why I don't have any sort of non-decreasing kind of constraint here. In a partial traversal, it's a continuous map that does not have to be surjective. So you can only traverse part of graph. You don't have to traverse all of the graph. So with these definitions, given two geometric graphs H and G, we define the social distancing width between these two graphs to be the supremum over all H and G of the closest, these 2 points, these two traversals come at any time t. And the story here is that one of these is a full traversal and the other is a partial traversal. So H is a full traversal of the graph capital H, because that is the graph where red is, and red is basically on a mission and it has to traverse it completely in some order. So it has to visit all of this graph capital H. Blue, on the other hand, is on G, and blue is just trying to stay away. So blue doesn't have to traverse all of G, which is why this function G is just required to be a partial traverse. Okay. And you can define other variants, but this is the one is most closely related to the traversal distance in the paper I mentioned in the last slide. And uh, one point to note is here the distance can again both be Euclidean or it can be geodesic. Uh, if so there's two variants, and finally you can define the social distancing width of one graph as the social distance width between the graph and itself. So, so this is the social distancing width of a graph, similar to how we define the social distancing width of a polygon. And what we show is both of these can basically be computed in quadratic time. So this can be computed in a time proportional to the product of the size of the graph, and this can be computed in time proportional to the square of the size of the graph for both Euclidean and geodesic versions. But it's open. So the lower bounds in this case are open, and while trying to prove lower bounds, we were considering special cases. And I will end with one interesting special case, which is that of a tree. So what is the social distance width of a tree? So imagine that red and blue are both walking on tree, and both red and blue move around T in a depth first fashion all their life. So the reason why we're considering it is if you basically take a small neighborhood of the tree, right? So that gives you a polygon, and this motion that I just described is the limiting motion of them moving around the boundary of that polygon that is just the thickened version of the tree. So red and blue are moving around T in a depth first fashion. How far can blue be? But turns out this you can compute in linear time. And to see why, first let's consider the case of a star. So let's say you have a star. So a star is just, it has a center and it has like these spokes to a bunch of other vertices. And turns out for star, what is the thing of most interest are the three longest spokes. So if this is the longest spoke, let's say this is the second longest, and that's the third longest spoke. So let's call these three spokes A, B, and C. So let's say R is the center of the star. What turns out the answer for a star is this third longest, is the length of this third longest spoke. So what you can show is that blue can maintain this distance, which is the length of the third longest spoke, by basically staying one spoke behind red. And this is actually optimal for the star. And you can generalize this to any arbitrary tree. So the claim is that the social distance width of a tree can be computed in linear time. And the answer for a tree is so-called the largest two outlier radius. So what is the two outlier radius? So suppose R is any vertex in a tree. If you remove R from tree, you get a bunch of smaller trees. And for any vertex V, let's say TV is the smaller tree where V would lie, were R to be deleted. So for example, if this is a vertex A, then sort of this is the component, and this is the tree TA that A would be in were I to delete R. So we'll have A to be the vertex that is farthest from R in the tree, B to be the vertex that is in the complement of TA that is farthest from R. So if you remove this entire tree that A lies in, after that, which is the vertex that is farthest from R, so we'll call that B. So this is analogous to the second longest spoke in our version of the star. And similarly, C is the third longest spoke. So it is the vertex of the tree minus TA and TB that is farthest from R. So we'll call RC the two outlier radius of R, and you find R star for which this two outlier radius is the largest, and you basically output the largest two outlier radius, and turns out this is the answer for a tree, and this can be computed in linear time. So that's interesting that if you find lower bounds, they will certainly, you cannot have quadratic conditional lower bounds for trees. So they must use the fact that your graph has cycles. And so that is all I have to say about the three settings. And there's tons of open problems here. It's basically, it's a flipped version of Frechet, and Frechet has so much work behind it that you can make many open problems. The ones most interesting to us are their subquadratic time constant factor approximations. So we don't know that, or can we? If there aren't, then is there a better hardness of approximation? Some polygon and graph versions, as I mentioned, we don't have hardness, and the one of the major open problems is what can you say about multiple agents who are all trying to sort of stay socially distant from each other. And that will be all. And I'm happy to take any questions, and thanks for listening.
Thank you very much. Try to maybe unmute and clap or make some other interesting sounds. And if anyone wants to ask a question, please unmute yourself and ask a question. Any questions at all?
So I have a question. Can you say anything special about the polygonal case when the polygons are rectilinear or orthogonal?
No, that's a good question. We haven't considered rectilinear versions. I know for Frechet there are results that beat the quadratic barrier for special cases of curve, but we haven't considered for the social distancing measure. That's an interesting setting.
So maybe I can ask the usual, what happens in 3 dimensions? In particular, for the curve case, if you have polygonal curves, even for the decision problem, what do you know?
So let's see. No, we don't know anything. We haven't considered this. But the free space diagram, so you have 2 polygonal curves in 3D. So I think the main question is whether the phase diagram will still have the properties that we want. And if it does,
Right.
then we should be able to build a reachability graph. I'm not sure. Do you know what the result is for Frechet? Is that computable in 3D?
That would be a good place to start, but I don't know the answer.
So so if my guess would be if Frechet is done, then this should be doable too, because it's.
I had the impression that there is no fundamental difference in higher dimensions. It has to do with the fact that you're working with a metric, so you probably have a convex set of.
Exactly. So then I think this would also generalize to higher dimensions. But I mean curves in polygonal curves in high dimensions, not higher dimensional surfaces.
But this might also give some additional flexibility in the lower bound argument.
Certainly, yes. If the 1D. So let me show where is my. A moment. Right. So I think in this slide, so the 1D proof is sort of it took more work, and we don't have, and it didn't give us an approximation factor. And so you're right. The lower the dimension is in which we're trying to prove hardness, the harder the hardness proof becomes. So 3D may be able to give us an easier proof or a better approximation factor.
Could I also ask, just for this decision problem, so let's suppose that you can maintain social distance 1.
Mm-hmm.
Can you say something about, let's suppose that the agents move with speed bounded by 1. Can you say something about the shortest time to actually achieve the desired motion, maintaining social distance 1?
No. So the bounded speed versions. So bounded speed basically translates to your path in the free space being of a bounded slope, right? And I think that is something that we haven't yet considered. I think I briefly tried to look at the fresh air literature, and seems like bounded speed is sort of a difficult area there too. And that's certainly one thing that Joe and I do want to look at next, both bounded speed for our setting. But
I mean, that was a question I had posed in a few settings, even for the ordinary Frichet, trying to get a minimum make span execution of the dog being walked.
Yeah.
Yeah. Are you aware of any results on that, David?
No, I'm not. I mean, I guess I'm thinking, what are the implications of this for, robot motion, or well separated robot motion, and yeah, I just don't know. I mean, it seems like it would be interesting to
certainly,
know more.
there's this challenge that's going on that's also potentially related, right? I don't know, it's called the CG challenge, where they're moving these pixels from starting point to endpoint, and pixels can't overlap. It's sort of related to the multi-agent version of social distancing in a way.
Yeah, that's exactly where it came from. In fact, it grew out of work that Valentin and I had done on this air traffic management, trying to, get flights completed as soon as possible.
Mm-hmm.
Yeah. Anyway, it was great talk.